Every single time you send a message or buy something online or even just connect to Wi-Fi, there's this invisible lock working in the background, keeping you safe. It's one of the most critical pieces of technology in our world, and yet most of us never even notice it's there. So today, we're going to pick that lock and see what's inside. So let me just ask you, what do you think is standing between your private information and, well, everyone else? What's the thing that's actually securing your bank details, your private messages, pretty much your whole digital life? It's a really good question. And the answer? It's both shockingly simple and incredibly deep. And there it is, AES, the Advanced Encryption Standard. This is the gold standard, the global benchmark for security. It's the algorithm that governments, massive corporations, and literally billions of us trust every single day. All right, let's get into it. So to really wrap our heads around AES, we've got to start at the very beginning. Where did this thing even come from, and what is it, really? Okay, so picture this. It's 1997, and the digital world's main security lock, something called DES, it was getting old and weak. So the U.S. National Institute of Standards and Technology, NIST, put out a call to the entire world. We need a new lock. It was a global competition. And after years of intense testing, this brilliant algorithm from two Belgian cryptographers called Rijndale came out on top. By 2001, it was officially crowned the new king, AES. At its heart, AES is what we call a block cipher. So instead of encrypting your data one little bit at a time, it chunks it up into these fixed-size blocks, always 128 bits, and then encrypts each block individually. And a huge part of its power is that it's flexible. It can use different key sizes, 128, 192, or 256 bits. And it's pretty simple. The longer the key, the tougher it is to crack. All right, now for the really cool part. How does this thing actually work? We're about to top the hood and peek inside this incredible mathematical machine that turns perfectly readable information into absolute gibberish for anyone who doesn't have the secret key. The entire strategy behind AES, the whole game really, boils down to two key ideas: confusion and diffusion. The goal is to make the relationship between the key you use and the scrambled text so incredibly complicated, so mixed up, that it becomes impossible to see any pattern at all. It does this using a clever structure called a substitution permutation network. Now here's where the magic happens. AES doesn't just scramble your data once. Oh no, it does it again and again and again, in a series of rounds. In every single round, it performs these 4 steps. It mixes in a piece of the secret key, it swaps out bytes for other bytes, it shifts rows of data around, and then it mixes up the columns. Just imagine shuffling a deck of cards using a super specific secret method, and then doing that 10 or 12 or even 14 more times. After all that, the original order is just gone. So we have this unbelievably strong mathematical process. But being strong is only half the battle, right? For it to become a global standard, it also had to be fast and practical. So let's take a look at how AES actually performs out there in the real world. And practical it was. A huge reason AES won that competition was its mind-blowing efficiency. I mean, just to put this into perspective, even on a processor from the year 2000, a Pentium 3 for crying out loud, it could encrypt data at these incredible speeds. It was this amazing combination of Fort Knox security and race car performance that made it perfect for, well, everything. But, and this is important, AES isn't the magic bullet for absolutely everything. For those super tiny low-power devices, think RFID tags or little IoT sensors, even super optimized AES is just too big and bulky. Its code footprint is just too large. And that's why a whole new class of lightweight ciphers was created, designed just for those tiny environments. It's all about using the right tool for the right job. Today, AES is so much more than just an algorithm. It's like a fundamental Lego brick for all of modern security. You find it in advanced modes like AES GCM, which not only encrypts your data, but also checks to make sure it hasn't been tampered with. It's the engine that secures our high-speed networks, and it's a core piece of TLS 1.3. That's the protocol that protects pretty much all the web traffic you use every single day. Okay, so for any encryption standard, there's always the ultimate question. Can it be broken? And this is where the conversation gets really, really interesting, because the answer totally depends on what you mean by broken. And this, right here, is probably the single most important concept to grasp in real-world security. You have to separate the pure, beautiful math of the AES algorithm from the way it's actually written into code and runs on a physical computer chip, because those are two very different things and they have completely different weaknesses. Believe me, cryptographers have thrown the kitchen sink at AES. And yeah, they've found some theoretical cracks. They've broken simpler versions with fewer rounds. There's even a known attack on full-strength AES 256. But the number of operations it needs is just astronomical. We're talking 2 to the power of 99.5. It's a number so big, it's basically impossible to do. So these are fascinating from an academic perspective, but they pose zero real-world threat. But then there's this. This quote is talking about a totally different kind of attack. One that doesn't care about the math. It targets the physical computer it's running on. It's called a side-channel attack. By just watching things like power usage or tiny timing differences, attackers can actually pull the secret key right out. And these attacks are not theoretical. They are very real, very practical, and as you can see, terrifyingly fast. And that really brings us to the truth about modern cryptography. It's not some fortress you just build once and then walk away from. Not at all. It is a constant, never-ending battle, a cat-and-mouse game between the people who build the locks and the people who try to pick them. So, what's the big takeaway here? It's this. The mathematical design of AES is a work of art. It's tough, it's resilient, it's beautiful. But all that amazing math means absolutely nothing if it's implemented poorly. Real-world security, the kind that actually protects you, depends entirely on careful, meticulous coding and hardware design to defend against those sneaky side-channel attacks. For over 2 decades, AES has been an incredible guardian for our digital world. But technology never stops moving. The looming threat of quantum computing, for instance, could one day break the kind of encryption we rely on today. And that leaves us with one final, really important question to ponder. As strong as AES is today, what comes next? What's going to be the invisible lock that protects all of us tomorrow?